Okay, let me get started. Um, Last class we were talking about one-dimensional motion. An example is the sprint in the upper picture on this slide. And today's class we're going to move on to two-dimensional motion. So an example would be the football that gets punted in the lower slide. So in the upper slide, the interesting motion, although the motion is happening in three-dimensional space, the interesting motion is along a line, and it's one-dimensional motion. And then again, for the lower slide, although the football is moving through three-dimensional space, the interesting motion of the football is happening in a plane, is happening over a two-dimensional sheet. And so we're going to make this transition from the sort of simplest one-dimensional motion to more complicated two-dimensional motion beginning this class. Actually, this class, we're going to focus on a tool, a language that we need to develop, use, and it's called vectors, and we're going to be working with vectors. And in next class and beyond, we'll be exploring the motion itself. Okay, so this is all about vectors, and we're going to learn today mostly how we describe vectors, the language of vectors, and then also how we do arithmetic, how we add vectors. So specifically, I want to outline both a sort of graphical way of describing vectors, picturing vectors, so that's this item here, and a mathematical description for vectors, that we can be quantitative about vectors. And then we're going to look at some, second bullet here, we're going to look at some simple cases of adding vectors. We're going to add vectors when the vectors are parallel, when they're opposite one another, and when they're perpendicular to one another. Now, those are special cases of adding vectors, but they're actually very common cases of adding vectors. They're very important cases of adding vectors, and it's useful to know the shortcuts for adding vectors when you've got these simple arrangements of vectors with them being parallel or opposite or perpendicular to one another. And then we'll move on, this bullet here, to the general case, the general way in which you can add vectors. And this general case, this general way is, we'll use that if the vectors are neither parallel, opposite, or perpendicular. We'll be able to add together a pair of vectors that have any orientation with respect to one another, with respect to each other. So that's the plan there. And as we work through these topics, we're going to sort of look at a number of examples, a number of illustrations, because you kind of learn what vectors are and the arithmetic of vectors by working with vectors, by doing vector problems of vector arithmetic, vector addition. Before we actually discuss vectors, I just want to remind you of that distinction that we made between what we call vectors and what we call scalars. So as examples of vectors that now you've met, displacement is a vector, velocity is a vector, acceleration is a vector. So each of those quantities has a size or a magnitude, and also has a direction or an orientation. So velocity has a size, 10 miles per hour, 50 miles per hour, has a direction. You're heading north, you're heading east. And all of those three quantities we've been working with up to now, displacement, velocity, acceleration, are vectors, have size and direction. A scalar is a quantity that has only size, no direction. And mass is a classic example of a scalar. Mass is the example of the scalar we've already met. And so that's going to be a scalar that comes up, I'm sure, in almost every class. And adding scalars together, doing arithmetic with scalars is easy. It's easy to add 1 kilogram to 2 kilograms to get 3 kilograms. Adding vectors together is more difficult. It's harder to add a vector representing, say, 30 miles per hour in the direction north to another vector of 50 miles per hour in the direction of east. That's more complicated. And so that's a big subject for today. Okay, so on this slide, I'm going to just describe vectors. Let me just get the chat up quickly. Somehow that disappeared on me. So this slide is just about the language of vectors. And this is how we picture vectors sort of graphically. We picture them as what we call a line segment. Here it is over here in red. It's really just an arrow. I mean, line segment, directed line segment means an arrow. That arrow has a certain length. That arrow has a certain direction. And the length of the arrow is the magnitude of the vector. The direction of the arrow is the orientation of the vector. And here I've denoted that direction theta. And so you can denote vectors by their magnitude and the orientation, their direction, by the magnitude of v, and in this case, v the vector, and the angle of the vector v, the theta. There's a second language we'll use, and I've denoted it here and here. We can also specify a vector, describe a vector, by describing its x and y components. So its x and y components are that vector's kind of projection onto the horizontal and the vertical axes here. It's like the vector's shadow on the horizontal axis and on the vertical axis. So Vx is the projection on the horizontal axis, Vy is the projection on the vertical axis, and it's an alternative way we can describe vectors. So the important thing about vectors then, just to summarize here, is there are two distinct languages we'll be using to describe them. One where we specify the magnitude and direction. I've written it as v and theta here. And one where we specify the x and y components. I've written that as vx and vy here. And you can do this for all our types of vectors, the displacement, the velocity, acceleration vectors, and any other vectors we're going to meet. And so, for example, I could specify this vector over here as saying if it was a velocity vector, that its magnitude was 3 meters per second and its orientation, direction, was 30 degrees. This should say counterclockwise, actually. I'll correct this here. 30 degrees counterclockwise from the x-axis. So finally, over here on the top right, I've written down how we kind of translate between these two different languages, magnitude and direction, and x and y components for describing vectors. So over here on the top right, think of this as like a little dictionary. but it's not like a Spanish-English dictionary. It's a dictionary that tells you how to convert from magnitude and direction to X and Y component language, or vice versa, from X and Y component language to magnitude and direction language. So, for example, upstairs here, suppose you know the magnitude and the direction of a vector. That's a v and a theta, magnitude and the direction. This tells you how, and you can see how it emerges for trigonometry over here, how to convert into the X and Y components of that vector. And then downstairs here, again, for this particular vector drawn over here, it's telling us how to convert from, this time from X and Y components, which are on the on the right-hand side, to the magnitude and direction on the right-hand side. So this upper equation here is Pythagoras' theorem. So again, it's just a little bit of geometry applied to this triangle over here. And then this is the angle in this corner down here, which is the inverse tangent of the opposite over the adjacent. So this is just a little bit of trigonometry here. So trigonometry and geometry allow us to step between the two different languages and use the two different languages interchangeably when one's more useful than the other, or the other is more useful than the first one. Okay, so that's just introduced for you the languages that we use for vectors, mathematical languages, and how we sketch vectors. Just a little word on notation. In different books and different instructors sometimes use different notations for vectors. So for me, you'll see in these overheads that I use this notation here. A vector is underlined. You see, many instructors will use this notation over here. A vector is overlined. And then in many textbooks, you'll see this notation here where this V is bold, and that means it's a vector. And so you'll see all of these three types of notations probably over this semester for vectors. And so just need to be aware of that. We couldn't, for some reason, we can't all agree on what's right. And obviously, bold works in a textbook, but not on a whiteboard. And so that's part of the reason. Okay, so let's look at some special cases of adding up vectors. The first case is parallel vectors, then we'll move on to opposite vectors, and then we'll move on to perpendicular vectors. So upstairs here, I'm picturing the addition of two vectors. So there's the first vector, I labeled it 1 with this subscript 1. Second vector, I labeled it 2 with this subscript 2. And I'm interested in the addition of these two vectors to make a resulting vector. And that's why I labeled it with R for resulting. So the way to picture vector additions, that's the first thing, is that the way you picture adding together V1 and V2 is by drawing V1, I've done that here, and then drawing V2 with its tail at the tip of V1. So it's kind of like head to toe, V1's head to V2's toe. And then if you draw the two vectors like this, the two that you're adding together like this, the resulting vector runs from the tail of the first vector, so way over here on the left, to the very tip of the second vector, way over here on the right. And so that red arrow is a vector, that's the resulting vector. And so that's how you picture the addition of vectors. Now, what I'm going to do is look at an example of two vectors. So we're going to imagine I brought a couple of ants to class today, and they're going to help us with these demonstrations, actually a few ants. And in this case, we're told that, in this example, that ant walks 2.5 meters north, and later she walks 1.5 meters north. And we're asked, what is the displacement vector for the ant's entire trip? So we're told the displacement vector for the two stages of the trip, the first part of the walk, second part of the walk. We got to figure out the total displacement vector. Okay, so the first thing I would do is draw out the vector addition. And look, these two stages of this ant's walk are both in the north direction. So this is a case of parallel vectors. And so here's the first vector, and its magnitude was 2.5 meters. So I wrote that down here. The little vertical lines here denote the size of, the magnitude of. And so its magnitude is 2.5 meters. And then this is the second vector, V2. I've drawn it, and again, I've written down its magnitude, its size is 1.5 meters. And I've actually drawn it, drawn these two vectors out as if I am adding them, because I put the second vector at the its toes on the head of the first vector. So head to toe here. And then the resulting vector, as I said, that is the sum of the two, goes from the tail of the first vector to the tip of the second vector. So that's picturing the addition. And if we want to calculate the addition for this special case, well, the magnitude for parallel vectors, the magnitude of the resultant is simply the sum of the magnitudes of the two individual vectors. So in this case, that would be 1.5 and 2.5 meters. 2.5 meters is the magnitude of the first one. 1.5 is the magnitude of the second one. They add up to a total magnitude for the resulting vector of 4 meters. And for the case of parallel vectors, where V1 and V2 are in the same direction, the resulting vector is always in the same direction as well. So that's simple. And I think that's, to me, that's sort of like common sense. If I didn't teach you anything about vectors other than their little arrows, and I said, add up these two arrows, that's what you would do. You didn't need me to do this for you. You already knew it. Okay, so now I want to go on to a second important case, which is adding together vectors in opposite directions. So that's like one's going north and one's going south, or one's going east and one's going west. And so I've pictured that case upstairs here. And I've drawn that picture of the vector addition of two opposite vectors in the same sort of way as I drew the vector addition of two parallel vectors. So I drew the first vector, V1, it's the longer arrow here. Then I drew the second vector, V2, it's the shorter arrow here. And I drew V2 with its toes on the head of V1. So again, that's how we draw the addition of these two vectors. And then I followed the same rule about the resulting vector. That's the one in red. The sum of those two vectors, the resulting vector, runs from the toes of the first one to the head of the second one. And so this is the resulting vector. And so that's how you picture the addition of opposite vectors. They sort of partially cancel each other out, and in some cases can completely cancel each other out. And let's look at an example of calculating the addition of two opposite vectors. So in this little example, we got the ants have come back. It's a different ant because this one's a he and the other one was a she. Another ant walks 2.5 meters northeast, then walks 1.5 meters southwest. What's the resulting displacement for the entire trip? So this is a case of two opposite vectors now. Northeast and southwest are opposite directions. And so we're adding together two vectors that point in opposite directions. So let's see if we can do this. Okay, so the first thing I did was to draw out the vector addition. So in this picture, just to be clear, I'm imagining that over here is northeast. That's towards the right in the picture. And over here is southwest. That's towards the left in the picture. So I drew the first vector. Its length was 2.5 meters. Magnitude is 2.5 meters, and it points towards the northeast. I drew the second vector. Its magnitude is 1.5 meters, and it points towards the southwest. And because I'm thinking of the addition, I drew the second vector's toes on the head of the first vector. And then the resulting vector is this guy here, VR, running from the tail of the first to the tip of the second. And now we just got to do the mathematics of adding up those two oppositely directed vectors. So we want to figure out the magnitude and the direction of this resulting vector here. So firstly, the magnitude. So when you have opposite vectors, and so this is a special case, but we'll meet it many times. Oops. The magnitude of the resulting vector is the difference between the size of the larger one and the size of the smaller one. In this case, V1 is the larger one, V2 is the smaller one. So in this case, the resulting vector's magnitude is 2.5 meters, the larger one, minus 1.5 meters, the smaller one. That's 1 meter. And so that's the magnitude of the resulting vector here. It's 1 meter long. I didn't really draw this perfectly accurately, but it is 1 meter long. The direction, what's the direction of the resulting vector? Well, the rule for the direction of the resulting vector when they're oppositely directed is it's in the direction of the larger vector, and it's opposite the direction of the smaller vector. So because V1 was the larger, it's in the same direction as V1. V2 was the smaller, so it's opposite the direction of the smaller one. And so that's that special case. Okay, so that wasn't that hard either. And I actually suspect you didn't need me to go through this slide either. You would just naturally know how to figure out the size of a resulting vector made out of, two oppositely directed vectors. And an interesting thing about it is that you can add two oppositely directed vectors that have non-zero magnitude and get a zero result. They can add to zero if they're oppositely directed. The other special case I wanted to look at was perpendicular vectors. And so here's the example for adding together two perpendicular vectors. So again, here's V1, the first vector that we want to add together, V2, the second vector that we want to add together, and these are at right angles to one another. There's 90 degrees between them. And again, if I'm drawing the addition of these two vectors, I'm going to use the same sort of recipe, the same rules. I'll draw the first vector, it's horizontal here. And then I'll draw the second vector, V2, it's vertical here. And the rule is I'm going to draw V2 with its toes on V1's head. And then the resulting vector, the combination of adding together those two individual vectors, that's VR, and it's going to run from the tail or the toes of the first vector to the tip or the head of the second vector. So the resulting vector looks like this. And it has a component that's horizontal, it has a component that's vertical. If you want the magnitude of that resulting vector, then you could see here, because this is a right angle triangle, this is the special case, perpendicular. The resulting vector is the hypotenuse of a right angle triangle. And so the square of its length is the sum of the squares of the other side's lengths. That's Pythagoras' theorem. So that's a bit of geometry over here. We mentioned it earlier. And if you want the direction of the resulting vector, I didn't mark that on here. Let's mark it. So I'm talking about this angle here. The direction of the resulting vector, well, again, think about the right angle triangle here. Think about the trigonometry that you love. And the angle in this corner is equal to the inverse tangent or arctangent. Old people call it arctangent. New people call it inverse tangent. So it's the inverse or arctangent of the ratio of the opposite side of the triangle to the adjacent side of the triangle. So the size of V2 over the size of V1. Know that supposing you wanted this angle, I'll call it another Greek symbol, phi r. The role of the opposite and the adjacent would reverse. And so you do have to be careful when thinking about these directions, these angles, and their relationship to the x and the y components. You do have to be careful about, you know, who's the opposite, who's the adjacent, because that determines who's in the numerator, who's in the denominator of this ratio here. Anyway, let's look at an example, an illustration of adding together two perpendicular vectors. So now a third ant comes by, and he or she walks 2.5 meters east, then 1.5 meters north. And we've got to figure out, again, the displacement vector for the entire trip. This is a case of perpendicular vectors, east direction, north direction, 90 degrees between them. So on this slide, I drew out the picture corresponding to that vector addition. Here's the 2.5 meter vector. Here's the second 1.5 meter vector. So in this picture, right, just to be clear, this direction is east, direction of the first vector. This direction going up is north, direction of the second vector. And so I use the rule that I put the second vector's toes on the head of the first vector, and the resulting vector runs from the toes of the first vector to the head of the second vector. So that's a picture of the vector addition, and now we just got to carry out the mathematics of adding two vectors together. So for the magnitude, the length of the red vector here, resulting vector here, the length squared is equal to the sum of the squares of the two other vectors. And so that will give us the length of the resulting vector. If you calculate 2.5 squared plus 1.5 squared and take the square root, is 2.9 meters. And if you want the direction, I'm going to figure out, again, this angle, not this angle theta r in my little right angle triangle. It's the length of the opposite side divided by the length of the adjacent side according to trigonometry. And so we got 1.5 meters divided by 2.5 meters, and that comes out to be 31 degrees. And so that's an example of adding together perpendicular vectors. And I spent time going through those three special cases. You might wonder, why so much time on these three special cases? You'll discover that so often, it's probably most of the time, we're adding vectors that fall into these special cases. And it's less usual that we meet vectors that are pointing in some other non-parallel, opposite, or at right angles directions to one another. So these are very important, and it's handy to be able to think about them and add them quickly. Okay, I should say a few words about tangent, because we were using tangent in the last slide, and we'll use it in later slides. And I think of it as the, if I think of the trigonometric functions, sine, cosine, and tan, I think of them like a little family. And like any, family, well, like my family, right? There's someone that we've elected as the naughty member of the family, or the troublemaker in the family. And tan, I would say, is the troublemaker in the trigonometric family. And the reason I say that is for a couple of reasons. So on this graph, I've drawn the tan function. Well, this is a graph where the vertical axis y is equal to the tangent of theta. So that's what I'm graphing here. So horizontally is theta, and vertically is the tangent of theta. And if you look at the horizontal axis, right, it goes from 0 is right here. There's 90 degrees, that's a right angle. There's 180 degrees. So there's 360 degrees here. You're going around completely around a circle over here. And then you could go the other direction, right? There's 90 degrees in the opposite direction. And if you keep going, you've gone around one complete circle here, 360 degrees, but counterclockwise, say, versus clockwise. Now, the solid lines are the tan function. So each of these little curves here, they're a nice shape to them. They kind of go up steeply, get shallower, go up steeply again. And they keep repeating. This pattern keeps repeating. And that's the tan function. But it's naughty, or can be tricky in the sense of two things. Firstly, tan has positive and negative infinities in it. So 0 degrees, right? There's a positive and negative infinity as you approach 0 degrees from either side. And other angles, right? These locations of these vertical dashed lines, those correspond to infinities in the tan function. So that's a sort of bad boy feature to it. But the worst one is, the one that will catch us out more, is that it's a multi-valued function. And what I mean by that is, let's take an example of the tangent of theta being 0.6. So imagine tan theta is 0.6. That corresponds not to one theta, but actually to a whole bunch of thetas. Look at them all. And there's more and more, right? There's some over here that are falling off the right end of the plot, and some over here that are falling off the left end of the plot, and it goes on forever and ever. So when you are calculating theta, knowing the tangent of theta, you have to remember that your calculator might give you one value. Supposing it gives you this guy here. Your calculator says it's this guy here, or this guy here. There are actually a whole family of them. There's a whole family of them that are separated by 180 degrees. And so that's an important feature of the tan function. And that will, it catches me out, it'll probably catch you out. We have to be careful about the multi-valued nature of the tan function when we're doing vector addition. Okay, I want to do a lecture quiz. Okay, so the correct answer of those sketches is the one in the top left. It's this guy here. Your answer may not have appeared as A or B or C. It could be any one of these, so forget that. It's this one here. And the way to think about that is first draw A. That's the first vector. It looks something like that. Then draw B. It's the second vector. Looks something like that. And I've drawn B with its toes on A's head. And then the resulting vector runs from the toes of the first vector A to the tip of the second vector B. So this is this guy here that goes horizontally from left to right. That is A plus B. And I'm just showing you here another notation for vectors where you put a little arrow on the head of the letters representing the vectors. Okay, so let's move on. And let's move on now to adding together vectors that are neither parallel, perpendicular, or opposite. And the first thing the only thing I'm doing on this slide is just reminding you, because we're going to use this a lot now, that we have these two languages for describing vectors. One is magnitude and direction, V and theta. And the other one is X and Y components, Vx and Vy. And so we can use the X and Y component language, we can use the magnitude and direction language when one's easier to work with or the other's easier to work with, and we can easily convert between the languages based on this little dictionary, which is just based on geometry and trigonometry. Okay, so the general addition of two vectors. So that this method works for any orientation of the vectors. And so let me just start by sketching that sort of addition. So here again, I'm sketching two vectors being added up. There's V1 over here on the left, there's V2 over here on the right. And I'm using the same rule for drawing their vector addition. So I draw the first vector, that's V1. I draw the second vector, V2. I put the toes of the second vector on the head of the first vector, and then the resulting vector, that's VR, runs from the tail of the first vector over here on the top left to the tip of the second vector over here on the bottom right. Also, I've added on this picture, you notice the X and Y, the horizontal components of the vectors, both the vector V1, the vector V2, and also the resulting vector. I've sketched those horizontal components here. And those are going to be important in adding up these vectors. So the key thing about adding together vectors, we want to add mathematically V1 and V2 to make the resulting vector, is that the addition of their components is simple addition, just like adding numbers, just like adding scalars. So I can find the resulting vector's X component by just adding together the two individual X components. I can find the resulting vector's Y component by just adding together the two individual vectors' Y components. And so we do the vector addition for these general cases. We do the addition itself in the languages of X and Y components. Now, you might start out knowing the magnitude and direction of the vectors, so you would have to convert to X and Y components. And you might want the magnitude and direction of the resulting vectors, so you might want to have to convert back to magnitude and direction. But the vector addition itself is done in X and Y component language, because that's just like adding ordinary numbers. It's just adding scalar quantities. And so that's how we're going to do it, basically. So let's look at an example of it. Okay, so, I mean, this is kind of topical, except my hurricane's going over Miami, not Houston or whatever. But anyway, I want to look at an example of adding together two displacement vectors. So in this problem, we're told that a hurricane's eye passes over Miami with a speed of 40 kilometers an hour and a direction 60 degrees west of north. So we're kind of told a velocity vector there. Then we're told that 3 hours later, the hurricane slows down to just 23 kilometers an hour and shifts to be directed in the northerly direction. So that's a second velocity vector. And then we're asked, how far from Miami is the hurricane or hurricane's eye after 4.5 hours? So we're told two velocity vectors, and we're told two time intervals, and we want to calculate the total displacement. And this problem involves the relationship between velocity and displacement, but more importantly here, it involves adding together two displacement vectors. So let's see how this goes. So the first thing I wanted to do was draw the two individual displacement vectors when the hurricane was first traveling at 40 kilometers an hour and then at 23 kilometers an hour, and then how they add together to make the total displacement vector, just to picture that. And then we can worry about the addition of the displacement vectors. So the first thing I did actually upstairs here, oh, got a bit out of control there. How do I go back? The first thing I did, I wrote down the numbers that we were given in the problem. So during the first stage of the trip, we were told it's at 40 kilometers an hour for 3 hours. And for the second stage of the trip, it was 23 kilometers an hour for actually an hour and a half. This shouldn't be 5.6, this should be 5.0. And so those are the numbers that we were given in the problem. And I called that first stage, I put little labels 1 on it, and second stage, little labels 2 on it. And so those are the V1s, V2s, T1s, T2s. I actually want the displacement vectors corresponding to the two stages of the trip. And the length of the displacement vectors, based on the definition of velocity or the relationship between velocity and displacement, the length of the displacement vectors, d1, d2, is just the product of the corresponding velocities and the time elapsed. So, you know, if you're traveling at a certain speed, if you make it larger, you're going to go further. If you're traveling for a certain time, if you make it longer, you're going to go further. So these equations describe that. So if I want the length of the first displacement vector, I multiply its velocity times the 3 hours. If I want the length of the second displacement vector, I multiply its velocity multiplied by 1.5 hours. And so that's all I did over here. Look, the speed times the time gives me 120 kilometers for the first displacement vector. Speed times time gives me just under 35 kilometers for the second displacement vector. And so I know the lengths of the displacement vectors. I do know their directions, right? I was told their directions in the question. And I think the direction of, this one was northwest. That's the first displacement. And then the second one was due north. That's the second displacement. And so then I went over here with this information that really I was, given in the problem. With that information, I drew out a sort of sketch of the vector addition. So here is D1 is the first displacement vector, and it's 120 kilometers long, and it's 60 degrees, we're told this in the problem, west of due north. And so that's the direction, θ1. And then the second displacement vector, here it is D2, is due north, and it's 35 kilometers long. And then the resulting runs from the tail of the first to the tip of the second when I draw the toes of the second on the head of the first. And so that was my first stage, just to picture the vector addition that's going on here. So now let's get on with the actual vector addition. And so we said that the way we do the vector addition is to add up the x components of the two vectors, add up the y components of the two vectors. And so my first job, my first step here is actually not doing addition of vectors, but changing the language of the first two vectors. We know their magnitudes and directions. I've got to figure out their x and y components. And so I'm doing that on this slide. Let me show you how to do that for these two vectors. So I drew D1. Here's D1. It's sort of northwest. And we know its size, 120 kilometers, and we know its direction, 60 degrees from north. And then I drew, to form a right-angle triangle, the x, the horizontal, and the y, the vertical components of it. And then I looked at that diagram and I said that the x component, which for this angle here is opposite the angle, is going to be obtained by taking the sine of the angle. This is a little bit of trigonometry here. And that the vertical component, the y component, which is adjacent the angle, we're going to get that by taking the cosine. And so if I multiply the cosine of theta by the magnitude of the vector, I'm going to get the length of this side here. And if I take the sine of theta times the magnitude of this vector, I'm going to get the length of the vertical side here. And so in the region I'm marked in blue is just a little bit of trigonometry. But there's something else I had to be careful of. And I did this, that's not a very good arrow, I know. It's the plus and minus signs. When I look at my drawing, well, I've just figured out the size of the opposite and the size of the adjacent. But I want the x and y components. If towards the right is the positive x direction, then this vector is actually going in the negative x direction. And so I've put in this minus sign here, because this is the negative x direction. And if vertically upwards is the positive y direction, then this side, this vector is going in the positive y direction. And so I put in this, this plus sign by hand to describe that fact. So the trigonometry just gave me the magnitudes of the opposite and the adjacent. The plus and minus signs from the diagram give me whether it's in the positive or negative x direction, whether it's in the positive or negative y direction. So that was an important thing. But once I've got that, I just plug in the thetas, I plug in the lengths of the vectors, and I get out the x and y components. So that's the first vector. It's actually much simpler for the second vector. I mean, you can see the answer for the second vector. Look, the second vector is just straight in the y direction. It's straight up. There's no east-west component to it, no horizontal component to it. And so for the second vector, I didn't even need to calculate anything. I just said that there is no x component. There's only a y component. And the y component is the positive, is a plus because it's going up, not down, in the positive y direction, not the negative y direction. And its size is the magnitude of vector d2 itself. But anyway, here we've got the two components of each of the two vectors. So that was our first step. Okay, step two. Step two is now step two is now actually doing the addition of the two vectors. And so now we've got the vectors in their x and y component form, we can straightforwardly do the addition. Now somehow I've gone to another slide. Oh, now getting even worse here. Somehow I've got to go backwards. How am I going to go backwards here? Why is it not going backwards for me? Here we are. Okay, panic over, and back to trying to add together the two vectors. So as I say, this is kind of like step two. And I'm going to figure out the resulting vector's x component, the resulting vector's y component, by adding together the x components of the two individual vectors, adding together the y components of the two individual vectors. And so that's straightforward. That addition of vectors is straightforward. Now we're in x and y component language. So for the x component of the resulting vector, I'm going to add the x component of the first vector, which is minus 104 kilometers, to the x component of the second vector, which is 0. And so I get a minus 104 kilometers for the x component of the resulting. For the y component of the resulting vector, I'm going to add together the two y components. It's 60 kilometers for the first vector. It was 34.5 kilometers for the second vector. That makes 94 kilometers. And so these are the two components of the resulting vector. Final step that I did. Final step was to take that x and y components of the resulting vector and turn it back into a magnitude and a direction of the resulting vector. And that's going to be our final answer, because that's going to tell us how far the magnitude of the resulting vector is, how far the hurricane has traveled. So this is our final step 3. And again, this is not addition of the vectors. This is just changing the language of the vectors. Okay, so when we change the language of the vectors, now we're going in the opposite direction. We know the x and y components of the resulting vector. We want to find the magnitude and direction of the resulting vector. So for the magnitude of the vector, we're going to use Pythagoras' theorem, just a bit of geometry. The length of this red arrow here, the square of its length, is the sum of the squares of the horizontal vertical sides of this right angle triangle that together make a right angle triangle with the resulting vector. So the length of the horizontal side, that's 104 kilometers. The length of the vertical side, that's 95 kilometers. So it's roughly 100 square root of 104 squared plus 95 squared. And that comes out to be this number here. And so that's the magnitude of the resulting vector. That's how far from Miami the hurricane is. So that sort of answered the question. If we want the direction, well, we can use trigonometry to answer the direction. And when I answered the direction, I actually answered it in two different ways here, because these two different ways often crop up. So I could specify direction with respect to due north. So here's due north. That's this theta r. Or if I was thinking of the x and y components, horizontal and vertical directions, I could specify the direction with respect to the positive horizontal x-axis. How many degrees around counterclockwise from the positive x-axis is the hurricane's displacement vector? So depending on the question, you might be asked for either one of these. And so I'm just going to answer with both of these in this particular case. So if you want the direction of the resulting vector with respect to due north, just think about the right angle triangle here that you've formed. This angle is inside that triangle. And by trigonometry, that angle is the inverse tangent of the opposite side of the triangle, its size, divided by the adjacent side of the triangle, its size. And so I can get theta r, how many degrees away from due north, by taking the size of the opposite side and divide it by the size of the adjacent side. And so I did that here. And I got 48 degrees roughly. If you wanted this angle here, which is the angle from the positive x-axis, the way that you would get that is by taking the ratio of the x and y components and taking the inverse tangent of that. And that would naturally give you this angle here. And so that would be an alternative way of specifying the direction. That comes out to be 137 degrees, i.e. it's 90 degrees more than the 47 degrees compared to the direction of due north. Okay, so that's one example of addition of vectors. I see some questions going by the chat about the quiz and multiple attempts on the quiz. I'll mention that at the end of today's class. It is because now we're on credit. And while we weren't on credit for quizzes, I let you answer and find the answer, correct answer yourself. Okay, final little topic that I want to mention is that we've talked here about displacement vectors, but there are other types of vectors, as you know. So displacement vectors is probably the most common or the most everyday one to think about. Displacement vectors take you from one location to another location. But there are other types of vectors, and we mentioned, for example, velocity vectors and acceleration vectors. And actually, I'll mention here that there's also force vectors and momentum vectors. Now, those are a bit more abstract vectors, but as we come to try and understand motion, understand why things move the way they do, then we'll be talking much more about force vectors and momentum vectors. And so all the work that we've done today on displacement vectors and adding up displacement vectors also applies for adding velocity vectors, adding acceleration vectors, adding force vectors, and adding momentum vectors. And we might not know exactly what forces and momentum are right now, or we may well know what forces and momentum are, but we're going to work a lot later on with adding up force vectors and momentum vectors. And actually, I would say most of today's class will prepare us for adding up force vectors and momentum vectors. I wanted to show you a little video of addition of not a displacement vector, but a velocity vector, so that you could appreciate that the idea of adding vectors is not just about displacement vectors. It's about any type of quantity, physical quantity that has magnitude and direction. So I'm going to share a different, I'm going to stop sharing this one. And share a different screen over here. I'm capable. So I hope you're seeing a video. Now, you're not seeing very much in the video at the moment. What you want to look out for in this video is that we're going to be adding together two vectors. So one of them is going to be a little toy truck. And you can just see it upstairs here in the top left-hand side. That little red blob is a toy truck. And then, so that toy truck's going to be set in motion. So that's a velocity vector. It's going to be moving over a sheet of paper. And this white region here is actually a sheet of paper on the floor. And so the other motion that's going to happen is the motion of the sheet of, I'm going to pull the sheet of paper. And so the truck will be moving across the sheet of paper, but the sheet of paper will be moving over the floor. And if you want to know the motion of the truck across the floor, then you have to add together the motion of the truck across the paper and the motion of the paper across the floor. And so this is an example. This is a neat example of vector addition, of velocity vector addition. We're going to add the truck's velocity on the paper to the paper's velocity on the floor to see the truck moving, see the velocity of the truck across the floor. So those are the things to think about. And I'm probably going to play this a couple of times. There's actually three distinct types of addition that are going on here. And so I'll stop this a couple of times as we walk through it. In this first case, the truck is going to be moving left to right. See the little blue arrow here? It's going left to right on the paper. The paper is going to be moving from the top to the bottom, so downwards. So this is going to be a case of adding together perpendicular vectors, vectors with 90 degrees between them. And we should therefore expect to see the truck, when it's moving across the floor, to move both left to right and top to bottom across the floor. Its motion on the paper is left to right. The paper's motion on the floor is top to bottom. But the combination, the addition, the truck will move across the floor, both left to right and top to bottom. So let's just watch that. And so I hope you see there that the truck was moving on the paper horizontally. The paper was moving on the floor vertically. The combination of those, the addition of those two velocities, caused the truck to move diagonally downwards from left to right. And that's an example of vector addition. And we talked about that as one of our special cases of vector addition. I'm thinking I'll put this in slow motion. So the next one is going to be an example of adding together two vectors that are neither parallel or perpendicular, okay? Here's the truck upstairs, is traveling left to right. Here's the paper on the floor. It's going to be pulled both downwards and towards the left. And so in this particular section of the video, we're going to be adding together this left to right vector, this horizontal velocity vector, and this angled velocity vector that's both downwards and towards the left. And so let's see the vector addition of these two guys. So the truck gets on the paper here. We start pulling the paper, and you're seeing the truck moving across the floor, which is the superposition, the addition of the two types of motion. Motion of the truck on the paper and the paper on the floor. We got one more coming up. This is my favorite. So in this particular case, the truck is going to go from left to right across the floor. Sorry, left to right across the paper. The paper's going to be pulled in the opposite direction, from right to left across the floor. And we're going to see the motion of the truck across the floor as the addition of those two velocity vectors. So as you watch this, watch the paper moving towards the left, watch the truck moving towards the right, and you're going to be seeing the addition of those two oppositely directed velocity vectors. Here's one on the left, it's towards the right. Here's the one on the right, it's towards the left. And now we're adding up those two vectors, and they cancel each other out. The truck is literally stationary with respect to the floor. I mean, I love that little bit. It's better than a Quentin Tarantino movie. Well, I mean, it's not that good, but I thought it was pretty good. Okay, so now we're just going to run it through again. Remember, you're going to see three different additions. This is additions of perpendicular vectors, and you get an angled vector. And that was a special case that we met. Next one coming up is the general case. This is addition of two. These vectors are neither parallel, perpendicular, or opposite. And so we're going to watch that addition. But think about the components. You've got a horizontal component of the truck on the paper. You've got a horizontal and a vertical component of the paper on the floor, and they combine to make that net motion of the truck across the floor. And then finally, this is like the crowning glory of this demonstration, I think, adding together opposite vectors, where the truck's motion across the paper and the paper's motion across the floor cancel each other out, and the truck just sits there. It's brilliant. Okay. Let me stop sharing that. And let me return briefly to the slides. I've not returned to the slides, have I? Okay. So I tried to emphasize there that, you know, not just displacement vectors have to be added, and actually more often we're adding things like force vectors or things like momentum vectors as we work our way through this class. There's a second example of vector addition in the class slides here. I'm not going to go through it. It's a second addition of adding together vectors, but it's not displacement vectors. It's two velocity vectors. You can see them in this overhead here. Let me get annotating again. There's a vector here. It's a force vector. This guy that we're seeing from the helicopter is pulling upwards and towards the left. There's a second vector here. It's also a force vector. This woman over here is pulling up and towards the right. And you're asked to figure out the resulting force vector of these two pulls. It's going to look something like this by eye. It's the superposition, it's the combination, it's the addition of these two vectors. And this example in the slides, I'm giving you a free example, right? I'm not going to work it in class because I run out of time. But here's another illustration of adding together vectors where it's force vectors rather than displacement vectors. Okay, I'm going to finish there. In the next class, we're going to be moving on to two-dimensional motion. So we're going to be moving on to motion in two dimensions. This might be a football, right, over here, or this might be a basketball. And this curve is a parabola. And we're going to be thinking about and understanding this parabolic motion that we call projectile motion, that is like basketball motion or football motion. So that's next class.